4 days. If you go at higher distance, it's 27.7. It's not big change, but okay, slower going. And there is this gap of the data because the telescope on Sol, they have 2 telescopes. One is looking just the closer to the sun, 3 telescopes, closer to the sun. The other is looking from larger distance, and the third one is looking at a larger, extended distance. And from the result from the first to the second telescope, C1, called C1 and C2, there is an unexpected gap. Our spectrometer was looking just at that height. Then we decided to make observation just to fill that gap. Another thing that I want to tell you is that, just to mention, we make this study. We have long time series of data because we observe every day. We put all the data in line, then we have the time series. Assuming that the corona is rotating, we have at about 27 days the same feature return. Then we have observation at different latitudes, and we can study how long time it takes to turn at the same position, and then the rotation rate. This is not is a problem not so with a single solution, because to study the periodicity of the data is a quite complex problem. And one kind of approach in this kind of problem is to do not use just a single way to determine the results, but it is possible to use different methods and try to compare them. If at least 2 or 3 methods they have some agreement in the results, we are very confident that we are looking for someone that is real. In this case, we use a Longo-Scarborough normalized periodogram, the autocorrelation function, and the discrete autocorrelation function. The most common and famous and historically used is the autocorrelation function that measures the degree of linear correlation between time series equispaced, the delay in the signal. The limitation of the autocorrelation function is that we need the data equispaced, maybe a data like every day a single measure, or every hour. And you can easily understand that we do not have every day at the same time this information. Then to use autocorrelation, we need to interpolate the data. These other 2 methods, the normalized, the Longo-Scarborough normalized, allow to make the analysis on unevenly sampled data without making interpolation, as the discrete autocorrelation function. Just some detail. Here we have a typical Occitan time series. This is 1 year of data. You can see that we have a jump and decrease. It's about is monthly recurrence. Then we have this, there are brighter structures that are turning bad in our field of view each month. What we do is, first of all, we detrend this data, which means that we remove a trend that can be related to the fact that our satellite is not always at the same distance from the sun, but is little moving, that there is a linear trend. And then we make the logarithmic, in logarithmic shape, our data. You can see that it's more clear, more uniform, this signal. Then we apply this Longo-Scarborough that in principle, is a way to make a sinusoidal fit with a sine function of the data, with a sine function that have a frequency that means a period. And this is the power spectrum that we obtain. For example, from this time series, we normalized the series. I draw here the sinusoid that is given, that is designed with this period. This is the power spectrum. It takes a long time to speak about that, but it's a power spectrum where we can see which are the power in this sinusoid. You can see that we can find about 7.5 days, and we find also the harmonics, that is the half of the frequency. This is 14 days. Then this means that there is something that is recurring. This was just a method to be sure that we are not, the results are not from the method that we use, because as you saw, the method is not a direct measurement, but it needs some modeling. We apply also the autocorrelation function. So we got the time series, we interpolate the time series in order to have equispaced data, and we apply the function that is like that, and we found the time lag, the autocorrelation function with different time lag. We found a lot of peaks in the autocorrelation function, and the delay between the peaks gives the rotation period. We found that also in this case, I didn't put it on we found that the distance, this is our days, the distance between the peaks, we have different power peaks. We got all these peaks to make one, we get all the distance from this peak, and we get the average, the weighted average of the distance. This first peak is more important than the others that are lower power, but we found a period that is very close to the period obtained with long scatter. So we have two methods that allow to determine the same quantity. We apply this. This is the observation. This was made. This dashed area are the observation period of SOHO spacecraft. Then we continue there, but here there was a blackout due to the loss of the satellite. We lost the satellite in the 98, but they recovered. They were so smart to recover. Then, just want to say that I will show you the results just at the solar minimum. We was quite lucky when we sent SOHO, because the sun is not is in some way variable star, has a cycle, as you know, and there is a minimum and the maximum of the activity. This curve is the number of sunspots. Here is the period of minimum, here is the maximum. Now there has been another minimum and another maximum. Now we are going down to another minimum. What's the difference? The main commonly used variable to display what if we are at the maximum or the minimum is the number of sunspots. But in general, also the entire corona has a different topology at the minimum and the maximum. I say that we was lucky, because when we started the SOHO mission, the corona was at the minimum, and we know that it was not a question of luck or not, but it was a very uniform minimum. then we had a chance to study a corona that was like similar to the model, the simple model that we can make. You can see that at the minimum we have a bright equatorial region and dark polar regions. Then, if we start at the minimum, we get one height, for example. All the synoptic observation at this is at 1.5 solar radii from the center of the sun. We get all the latitude, and we can make the image for 1 year of data. This is UV emission for two lines. This is oxygen, this is hydrogen, for 1 year, from May to May, from 1 year of data. You can see by eye. I did this, a suggestion that I can say to you is that sometimes when you have astrophysical data, look at the data also just for curiosity, because it may be that you can discover something new and unexpected. And mainly this is more easy when you are young, because becoming older you start to look what you expect, because you have more things in your mind, and but someone say that there is this effect, then you go to look this effect. For example, I discovered, it's not a Nobel Prize discovery, but it was a nice discovery that I love to have a lot of citation in the publication that I did. The difference in the north of the north and the south, just a moment, of the pole, in the north and south pole, there are, you can just a little bit see, there are some that we call polar plumes. There are narrow feature brighter, and there are region darker between the plumes. Just for curiosity, I got the intensity of this region observed in the UVCS, in hydrogen line. I got a plot, and as expected, we found bright and dark, because there were different, it's like my head, no, I didn't have, like some small bright features. And just for curiosity, I plotted also the width of the lines. And I saw that where the lines are brighter, the widths are narrower. Then I got two lines, the two oxygen lines. I got this plot. Then I decided to make the plot of the ratio between the two lines. And I found that the ratio was anti-correlated too. I say, is just random things or is physical things? Frankly, I did that at the PhD time, and I saw that to my tutor. And my tutor said, but this is very important. You have to write down the paper soon. At the beginning, I didn't understand. I said, why? It's just a thing that I had no explanation of that. But in fact, the explanation was that I got to read some papers, some literature, that the bright feature, they was almost static, and the dark region between, there was dynamics. It means that there is a solar wind flowing between the two bright features. And this was an important result, and other people work on that. And it was discovered just looking at the data without having in mind what I was looking for. This is somewhat similar here. I make these synoptic maps just to look at another representation of the data. And you can see that there are recurrence of the bright feature. These are time, these are the position, polar position. And there are differences between the Lyman alpha and the oxygen. Then, making the study of the periodicity, we found this. That in this area, you can see this is the period. This is more than 28 days, and this is less than 28 days. Right? Speed up a little bit. No. Okay, this is a plot. It's the same plot but rotated. This is the latitude, means from here to here, from here to here. And this is the rotation period. You can clearly see that this is towards south. In this region, the rotation is more longer than in the north. These are a different height. This is at 1.5, this is a little higher, this is at 2 solar radii. And we see that the effect is observable at all these heights. Then we compare our rotation period with the sunspot. You know that the sun is not rotating as a solid body, as a differential rotation. Then the sunspot, they rotate faster at the equatorial latitude and slower at the mid latitude. We found that the corona is rotating in more uniform way, but is following the sunspot rotation. In this is equatorial, this is toward north and toward south. Is following the sunspot rotation in that region. Then there is some interpretation, but maybe not time to. Okay, just from point of view of data analysis, we make a comparison of the two techniques that we use. This is a longus carbon. This is the autocorrelation analysis. We can see that the autocorrelation analysis that requires to interpolate the data give the similar results with larger error bar. But the results are in some way similar. The results are comparable. Then this agreement allows us to decide that we are in the right road to find something that is physical. So, I thought about that. Another thing is that with our data, remember that I told that with visible light data, they make the measurement of the rotation, but they have a gap between two different instruments that was quite mysterious, this gap, because it is quite is a too steep gap. We got to look at this region with our instrument, because we are observing exactly at that, and we see that, in fact, this is in a different scale, the gap that I found from open square to. And we found that, in fact, we have this kind of gap. This place, just to mention some kind of explanation, is around 2.3, 2.5 solar radii. For some reason that is not to explain, is what we call surface region, where when we make the model of magnetic field, we need a surface because it's harder to go down, where we put a radial approximation of the surface. And is at that height, then this means that probably this height is a transition, is a real transition place of the condition of the magnetic corona. And this gap between the last results is real, and it was not an instrumental effect. Just to finish about the rotation, I did also this, that is quite colored, and this was in some way a joke. I didn't publish that result. Probably some other more aggressive than me in producing science, but they could publish, but it was like a joke, but it's interesting. What I did, I have a map of the Carrington map of the intensity of the line. I show you that. Just a moment. The intensity. Okay, this is the intensity map for 1 year, obtained by getting the spectra and making the Gaussian fitting. Then this is one of the parameters. I have also the centroid of the line and the width of the Gaussian line. Then what I did, I made also the image, the current of image map of another quantity. That is the line centroid. This is the line center. You can see that there are these strange and very rapid change in color. Means that the centroid it changes often for some long time. This is instrumental because we have our grating that can be rotated to send light on different portions of the detector. This is because if we send the light for a long time at the same position, we burn the detector and we have a very short lifetime of the detector. But moving this grating, we put the line in a different position of the detector. But if you remember, we have to make the Wepner calibration. The Wepner calibration is not so easy. Then, moving the line, we put in a position of the detector that is not well calibrated. But this is the reason because we have this larger change in color map. This is explained by that. If for this reason we use one position of the grating, then the lines falls always in the same area. Then we move to another position to preserve the detector. Another one, here we go back to the previous, and we do the same things, observing there, this is at the east limb, and observe it there. Then, if I make a map, the absolute value are very difficult to use. But if I get the map at the limb of the sun, and the other limb of the sun, and I expect that the sun is rotating in that direction. If we look at on the top of the sun, we can see the sun rotating like counterclockwise. So I expect that this limb, for Doppler effect, the plasma is moving toward us. From the other, the plasma is going farther. Then I expect that if I make the difference between these two centroids, I found the difference in the Doppler, which means the difference in which means the velocity of the rotation. I didn't publish this result because it's quite, I say, it's a tiny effect. Because this rotation is not so fast that the plasma is really fast flowing toward us, and the other rotation is not. Anyway, what is curious, maybe that I decided to put in a paper, if I make this difference, then I found a blue and red map. So this is the time, this is the latitude. I found this map. This is the difference east and west. It's not exactly blue or red. In fact, if I plot all the value, I found that the values are very scattered. Seems that there are no results. But if I made the average of this, I found that this is the difference on the wavelength. Delta lambda is not zero. It's not compensated. And if I convert the delta lambda in a frequency or in period, I found exactly 27.21 days, which is very close to the number that we expect. That is quite challenging, this method, because you can see that here there is a large scattering of the data, but if we make statistics, you found result. This is to finish. Now, sometimes the results are hidden in the statistics. If you make a lot of measurement and you perform the average and the estimate, I didn't put, frankly, is not finished the work, because I have to put here to be sure of that, plus minus the error bar. Maybe that I will be after this. So I stop here for now.
Yeah. Thank you, Silvio. So we have half an hour before lunch. We'd like to spend this half an hour with some discussion. The other thing we're going to do, I have here a folder called codes. Inside it has the codes that we're going to use, which is ideal codes, and the actual data that's already been downloaded. And we're going to look at the CME and a comment. Is that correct? Or?
Yeah, and
we're going to look at UPCS and ALASCO data. So what I would like to do, or would like you guys to do, please, for those who have downloaded, who have installed IDL in their laptops, to take the codes folder and put it in your machine. So after lunch, we can start working with that, hands-on, and working with the data. Okay?
I still have some slide on the CNE.
We would like, we can see, let's see if there is, without overwhelming them, let's see if they have questions about first the portion. Now the other thing, please, this is very interactive, meaning and also engaging. We don't want to go out and just go have lunch, and please, if you would like, you can have a session with Silvio or myself or whoever you want. This applies to anything. Sit together with lunch, talk about whatever questions you have during coffee break, after dinner.